Hello everyone. Thank you for coming. People in the meeting, watching on YouTube or viewing the the slides afterwards. Great start. I'm unable to share my screen, but that doesn't matter. I wasn't going to share anything too much interest. So to introduce myself, first of all, my name's David Ford. I'm a biochemistry scientist in the Ocean Forecasting Research and Development Group at the Met Office, but I'm also, along with Fraser Davidson at Environment Canada, a co-chair of the Operational Systems Working Group of OceanPredict, and it's in that capacity that I'm organising this session to try and push forward the discussion on best practices in ocean prediction. And this session is focusing particularly on regional ocean prediction, coming out of one of the key things that came out of a more general session on ocean forecasting we had at last year's best practices workshop. So we have 6 speakers giving very interesting talks, from focusing on specific regions through to Nadia and Enrique at the end, talking more generally from an ocean decade perspective. And then with luck, we'll have a bit of time at the end for some discussion. So if you're happy to go ahead, Jennifer.
Okay, David, how does that look? Are we?
Looks good.
Okay, great. So yeah, thanks for this invitation to give an update on South Africa's operational forecast developments. So I'm going to start with a little recap of where we were last year, but also a little bit of background on how we got there, because I think for us there was quite a lesson in that. So, for decades, primarily academics have been talking about operational ocean services, and how useful it would be, but it was only when it was ratified at quite a high level in Operations PECISA that was developed to really support the oceans economy and ongoing exploitation of our oceans to support our growing economy, that it came off the ground. And our Department of Forestry, Fisheries and the Environment were mandated with the Marine Protection Services and Ocean Governance workstream of this Operations PECISA. And to this end, they developed, in collaboration with the CSIR, the National Oceans and Coastal Information Management System, which provides, a portal for decision support tools for various stakeholders, really just to support the sustainable development and effective governance of South Africa's oceans and coasts in the light of the ongoing and continued exploitation of South Africa's oceans. So we had this beautiful front end, which provides tool for stakeholders, and an example of one of the tools. This is the Fisheries and Aquaculture tool that was developed in support of the aquaculture industry, which suffered an enormous loss in 2016 due to a harmful algal bloom event. So this tool has really been co-designed with the aquaculture industry, in which they provide us with in situ information, but also guidance as to what they require. It provides a matrix of probability of harmful algal blooms occurring in particular key locations. And this tool it uses optimized satellite information to provide this information for stakeholders. So this has really been an amazing exemplar of co-design with stakeholders. But until now, we have not had any, until that point, we had not had any optimized ocean forecast models for the South African coast integrated into this system. And the challenge here was that we didn't have enough capacity to do this. So this doesn't mean that we didn't need it. So we had to start somewhere, and our solution was to start small and to pick the low-hanging fruit. And the first thing we did was to add value to existing global forecast services. So for example, in this case, we used Copernicus Marine Services forecasts, and we developed metrics that were of interest to the South African ocean community, which include, for example, the core on the edges of the Agulhas Current, its transports, sea surface temperature anomalies, but also marine heat waves and eddy tracking tools, which we disseminated visually, operationally on a portal, on a website somewhere. And while this was a very, very simple approach, it's actually already proved useful in understanding the dynamics that was associated with an extreme and bizarre event in which a number of various marine species washed ashore, from sharks to rays and eels and so on. So it has already proved useful, even though it was really simple. So our next approach was to downscale global forecast services to provide optimized information for a high use area of our coastline. Now, this Algoa Bay area is really the epicenter of both land-based and coastal industry in South Africa. Also, it's on the cusp of the Agulhas Current, which actually is a shipping highway. And in this way, it adds a sheltered region where ships come in to bunker, so to refuel. So it's host also to an oil bunkering industry, but at the same time, it hosts one of our largest marine protected areas and important bird colonies. So it's really a contentious region and a high use area of our coastline. So we developed an operational forecast model using the Siemens forecasts as the ocean boundaries and the GFS atmospheric forecasts at the surface. Our grid is about 3 kilometers at the edges, and it increases to 500 meters within the center of the bay. We provide the user with surface variables that they're able to pick. They can pick any of the surface variables that they want to visualize. And we have a slider function that allows the user to, shift the time that they want to have a look at. So, while sea surface temperatures, salinity, sea surface height and currents animated in rainbow colors is visually appealing and pretty, it's only really academics who find it useful. So in order to make it more useful for the stakeholder on the ground in Algoa Bay, or at least to help them understand why they need this information, we developed a very rudimentary particle tracking tool in which we released a hypothetical oil spill every day at each of the oil bunkering sites. This was just to allow, the user to see where an oil spill might end up and what sort of resources they need to put out to, save the birds on the bird islands and so on. So we implemented this hypothetical oil spill, and it provided 5-day forecasts of the particle tracking. And, I think it was quite sweet and useful. And so we've developed something really simple. And given our limited capacity, we really did this in the spirit of a boer maak 'n plan, and that is Afrikaans for a farmer makes a plan. And what it really means is just to make something work, despite the shortage of resources, of having the right tools, and some might say it's a kind of brute force approach. But, we produced something and it proved to be useful. However, this approach did not lend itself to any considerations of best practices. We really just tried to get something working. So we didn't really think about best practices at all in terms of workflow standards or anything else. Also, just to say that none of this would have happened if we didn't have high-level buy-in or institutional buy-in via the high-level policy decisions that were made via Operations PAKISA. So for us, that was a crucial step in South Africa. So in the last year, we've upped our game quite a lot in this regard, particularly with respect to our best practices. We've totally refactored our full workflow solution, from the automated downloads to the dissemination the visualization and dissemination on a user portal. We've implemented the whole workflow on a GitHub that is automated. And our model tools are all Dockerized for the ease of redeployment. We learned the hard way that this is really important to do. Our server with the previous system crashed and we lost everything. So this is really a critical step, an important best practice, if you like. So the next thing we developed was a much more sophisticated user portal, which allows the user to toggle the various marine protected areas. They can zoom in or out. It's got our bathymetry there. It also allows the user to configure their color mapping and to edit the range and scale of the color bar. The user can select the depth. So it's not only surface variables, the user actually gets to toggle which depth they look at. Of course, they can select the variable that interests them. And if they click on any spot on the map, they will be given full information about all the variables at that location. So not only do we, along with our Algoa Bay model, we've also developed a secondary forecast model of an equally important area of the South African coastline that includes Table Bay and False Bay, but also the important aquaculture industry on the Southwest Cape Coast. Not only do we provide the models visually, we also provide it on a thread server. So our model outputs are operationally uploaded onto our thread server that is freely accessible by anyone, anywhere. So the last thing that we've done most recently is to implement a more sophisticated oil spill tracking solution using OpenDrift. The spill application takes many different oil types that takes into consideration various weathering characteristics and mixing within the water column. But we have also implemented the so-called leeway tracking module from OpenDrift, which allows the user to plant any kind of drift or up to 85 objects in the ocean and to track the trajectory. So we've implemented this not only within our downscaled solution, but also within the CMEMS boundaries with which we force our downscaled solution. And these are seamlessly connected. So for example, if there's an oil spill within the Agulhas current upstream of our downscale solution, it will seamlessly meet our high resolution domain and then get information from it in terms of where the oil spill will end up. So we have ongoing stakeholder engagement activities, and for me, this is an absolutely critical part of our workflow and our sustainability, because if we can't produce information that is useful to the stakeholders, we're not going to go very far or very long. So we have annual stakeholder engagement workshop meetings, as well as roadshows in other cities within South Africa. And finally, I'd just like to share that I think we've made good progress, but our list of things to do remains really long, and it gets longer by the day. But in the future, we endeavor to make all of our new developments guided by best practices. And this is so that we can support transparency, so people can really see what we're doing. There's nothing secret, there's no black box. To make our system interoperable, if we want to change servers or if we want to share with our under-resourced nations in Southern Africa, we want to support open science and also to support efficiency of our system. And this is all in partnership with various institutes in South Africa. I won't name them all, but here they are. And with that, I would like to thank you for your time.
Thank you very much. That was very interesting. If people have any questions, I'm not sure if people are able to speak, but please put them in the Q&A chat. If you're quick, I'll ask them in a minute. Otherwise, speakers can answer them in the Q&A. I just have one question. So in your stakeholder engagement, how do you go about prioritizing different user needs and what to go about addressing?
Well, we have different groups for each decision support tool. They're called tags, and I guess at each of these stakeholder engagement meetings, we would have a separate parallel session for search and rescue operations, for example. And those teams will focus on the needs of those particular stakeholders, and in their separate working groups, they will work on their needs separately. But in terms of prioritizing in particular, I think it's a combination of what's possible and within our capacity and resources. Stakeholders might need something that is really hard to achieve right now, but I think it's a matter of balancing their needs with what we can do.
Yeah, okay, thank you. Question in the chat from Jay. How do you quantify stakeholder acceptance and use?
Thanks, Jay, for the question. So that's been an ongoing discussion, and sometimes it's really easy, sometimes it's not so easy. So the example of the aquaculture industry, I think because they have been so integrally involved from the beginning, their engagement is quite easy to track as far as I know. I'm not really involved with that working group, but I think it's easy to see that they're taking up our information well. But in the case of our models, it's not so straightforward because we don't really know who is looking at our web portal. And that is something I would like to work on and develop some sort of, perhaps a login or something to that effect. But as far as I'm concerned, that's not really enough. You really, in order to know what kind of impact your information is having, I think you need to know more than just who is using your data. And that's an open question. And hopefully groups like this will help us to come up with a good solution for that. Thanks.
Yep, thank you. And yeah, just to say, I've experienced retention in other systems about having completely open science and not requiring any login or information, which will expand your use of it, but then you don't know who your customers are. And yeah, it's not one easy to resolve. But yeah, so thank you very much. If anyone has any more questions, please put them in the chat and hopefully Jennifer can answer them in writing. And Anita, are you happy to present next, please?
So good morning, and I'm Anitha from National Center for Coastal Research, and as well as I'm affiliated with National Center for Medium Range Weather Forecasting. This is from the Ministry of Earth Sciences, and the outline of my talk would be, a part would be on coupled biogeochemical modeling, and then I'll dwell mostly on the coastal applications and the BPs, and finally I'll conclude with challenges and gaps. So coupled biogeophysical modeling, we are doing at a regional scale for India, as well as very local scale. But the objectives, as I say, to understand the physical processes and predicting primary, secondary, as well as tertiary level production. But these objectives, the prediction objectives are still not operational. I will show because mostly the problem lies with, if you see, this is for the coast of India, where the upwelling is very important, and where subsurface hypoxic waters upwell during the southwest monsoon, and it is costing many livelihoods, about 14-15 million livelihoods. But we are unable to do it because when you see at the oxygen, dissolved oxygen, the way the models simulate them is this, because of lack of poor initialization. What we see is the qualitatively it is reproducing, but then quantitatively there's a lot of change, and magnitudes are quite different. So what we have tried to do is we try to put all the available data and try to initialize it, but then we had a lot of problems in preparing the initial nature. I think we need to come up with best practices for how we prepare initialization data sets for BGC. So that is one thing that I would say. And then we have a monitoring program where along the coast of India, we monitor on a seasonal basis, and then we give a report for the SDG India on the status of the water quality all Indian coast. So when I come to the application, the downstream applications, we have a few applications like coastal flooding, because Mumbai and this is Mumbai and this is Kolkata. They are the most exposed cities on the coast of India, which are the most ranked, top two ranked cities, and in 2070 as well. So for this, what we have come really with a very good early warning system for these two cities of Mumbai and Chennai, and we are right now also doing for Kolkata. So this involves many, right from the weather forecasting and forecasting, as well as the stakeholder, the end user will be the local administration. So we involve the socio-economics as well, models of weather to hydrology to hydrodynamics and the ocean models, all the models put together. And then we forecast not just the flood inundation in the city, but also the vulnerability and the risk. And these are not just only based on weather models. This early warning we gave for about 3 days in advance. And every day we give it, we issue the warnings, not only the warning, the flood inundation, the risk, and the vulnerability as well. And to make it foolproof, what we do is just not the weather models. We also parallelly have other fast running output based on real-time observations. These are all the AWS observations, collect the rainfall. And also we have the library cases, just in case how much rainfall, this amount of rain is falling on it, on the city of Mumbai or Chennai, and how long it lasts. So for heavy rainfall, very heavy rainfall, extreme cases, we have library cases just to have a ready reckoner for the administrator. So these are provided for the administrators at all levels, like district, ward. So the forecast is given at 40 meters, and then these are the wards, which are something like a few kilometers or few in extent. So for each of the ward, along with this, we combine the socioeconomics and say, these are the streets, even we go to an impact level assessment, like impact level forecast, like these are the streets, these are the number of streets, these are the number of statistics of the amenities that are, like how many hospitals are there, how many police stations are there. So all this will put it, and if an administrator who is at a ward level, he wants to generate this report only for the ward, he can do it for his own particular ward. But if as an administrator, he is for the entire region, like for the entire Mumbai region, he can just say which are the wards, and this also includes the details of dissemination, like who are the responsible people for each ward. So these are some good practices that is another. So coming to the second one, this is the coastal inundation risk atlas. So what we do is the risk we calculate, because from storm surge, all the number of cyclones, what is the level of sea level rise, and we take the contribution of each of this and produce what is the risk and how many villages or rural areas and how many people are associated with that. So this is a dashboard for that, and we can always put and slide, and there are slider options and many other options, like how many to select each of the wards, where are the fishing people fishing, and how many natural inundation how many natural what we have say safety measures that we have, how many artificial safety measures. So everything is combined in the coastal risk atlas, and there's a dashboard for this, and this is available for the administrators of the particular region for the entire Tamil Nadu coast. So what is the level of risk and all those things. And then the other thing that we have is this marine spatial that we are developing towards is marine spatial planning. This is not for the entire Indian coast, but it is only for the two pilot regions that we have selected for a Pondicherry. There's a small region in Tamil Nadu, near Tamil Nadu. So what we collect is first all the environmental, economic, and socio-economic data sets, and then we combine it with the modeling data sets, and then we map it. We have a spatial, and then we have this is the dashboard that we have. For example, a fisherman can say which is the fishing area, which is the fishing band area, or which is a cable line is there where fishing is not allowed, or so on and so forth. All the sectoral where tourism is there allowed, where are ecologically sensitive regions. So all this is given, and these are different applications for both the administrator as well as the fishermen also. So these are basically the marine spatial planning is for the administrator, and there's another one that we have developed for seagrass for suitability, site suitability. So we've mixed up all the biogeochemistry models, forecasts, and then the climatological data, and then we looked at this is a particular island near the Lakshadweep, near the Arabian Sea in Indian Ocean. So we have mixed, combined all these, and then we have come with criteria, selection criteria which are suitable, and then found out which are the sites suitable to. This is to advise the fishermen when they are not fishing, when fishing is banned, they can do, and alternatives for the very poor fishermen in the region. So this is the site suitability for cultivating seaweed cultivation. And then this MSP, we have a collaboration with the Norwegian government as well. And then we have the other one is Coastal Biogeography Information System. All the near the coast, all along the Indian coast, we are collecting all the systems, and we have a dashboard for this as well. All the biodiversity, biophysical variability, vulnerability, and all the things. And we are putting it in a digital coast for India, which is called DCoin. And finally, of course, this is a tracking marine litter. This is another application. We are developing this. And then finally there's a Thundil. This Thundil means the fishing rod. This is an app for Google app for fishermen. If they install it, then welcome it says, and then they can measure the distance their boat distance, who are all the boat, and what is the weather, what is the potential fishing zone. The potential fishing zone is given by our sister institute INCOIS, and then how many trips they're doing it, who are the crew on their boat, and everything is can be uploaded, and what is the lake view, what would be the weather, what would be the ocean state, and where zone is available. So everything they can do it from their port itself. This is the fisherman's app. So this is developed by NCCR in collaboration with the fisheries department, and they have an SOS as well. If there is something, an adverse incident, or if there's an oil slick, they can take a photograph and then upload it and send it. So this is one sort. So we do it in tandem with our basically Ministry of Earth Sciences is there. And I come from National Center for Coastal Research as well as NCMRWF. So these are these IMD, we do it with tandem with all the institutes, as well as this is only under the Ministry of Earth Sciences. IMD gives the weather forecasts, and NCMRWF gives the model forecasts. This is the SOP, the IMD gives the SOP, the weather forecast, the INCOIS, Indian National Center for Ocean Information, the open ocean model forecast for ocean forecasting is done, and the coastal forecasting is done at National Center for Coastal Research, and in collaboration with many other institutes like the state governments, because the administrators who are at the end are basically they are the state government administrators. So we do a lot of stakeholder meetings, and then we approach them with all our applications, and then do it. So towards the end, I have given some of the challenges that are in biogeochemical models, which are really very, if we have to go forward for forecasting this biogeochemistry right now, operationally, it doesn't seem to be very feasible, because we have a lot of gaps in the biogeochemical models like chlorophyll. There's no coastal data, and whatever coastal data is there, bacteria is not modeled. So we cannot give, one challenge is water quality modeling prediction, because the bacteria is not modeled properly. So there are a lot of challenges in modeling. And some of the other challenges in local scale models is there are lots of human interventions along the coast. And then do we have real-time river fluxes for the biogeochemical models? River fluxes, what we get is majorly only the monthly or the annual long-term means or something, especially when we come to the biogeochemical variables. It's really a lot, like we don't have any measurements at all. What is the flux of the nutrients that is coming from the rivers into the coast? So the coast is really a very complex place, and there are too many players, and there's lots of conflict resolutions that have to be sorted out for along with the stakeholders. So these are some of the issues and some of the best practices that I have put forward. So some of them can be synergized to observational and model experiments that we need to carry forward, and model intent comparisons and regular interaction between stakeholders. And then going ahead one step, do we really have, if it is a biogeochemistry, do we really have we have a lot of publications, and that data is not put together. We can also put together, because that's already a quality control data, through AI/ML and build a database for based on the literature search. If we have somebody is having, please do share. So from published literature, we can collate all the database and build a database from it for the course. So, and then we need to develop metrics, especially for the local scale BGC. So these are some of them. And thank you for your attention.
Thank you very much for that. I found that very interesting, and a lot of parallels with my work on biochemical forecasting at the Met Office. If anyone has any question, please put them in the chat or the Q&A. I will ask one based on my own interest. So for the coastal biogeochemistry, how much interaction do you have with fishers and users, and what variables or quantities do you feel they are after?
You mean the fisheries institutes? Yeah, we have a fisheries.
Fisheries but both of them are more widely.
Yeah, fisheries survey of India, we do get the data, like what are the species level. The only data that we get is the species level, but the biogeochemistry actual data, we don't have any. Only the scientific cruises, whatever we have, and the local administration does it as sort of an SOP for the water quality. But they are, I think they're not in digital form, some of them are, but quality is one thing that we cannot really rely upon. We really don't know. And how do we put all these together different, because they're measured by different instruments, different sensitivities. So these are, and we try to put one buoy at our coast, but then there is a very operationally, it's a challenging task for autonomous collection of this, because no sensor is really ready for the levels of pollution, or for the levels of nutrients in the coastal region. No autonomous sensors that we have seen in the industry is really ready for that. That is one thing. And vandalism and then biofouling, or really like every 15 days we needed to change the sensor. That's the sort of like expense that is involved in this. I hope I have answered the question.
Yeah, thank you. And we got one question in the chat. Where should one search for open data to collate and use for machine learning use for biogeochemical modeling?
So right now we don't have a database. I think we need to develop it. Like some of the AOPs, they do it. Adverse outcome. So chemistry, a lot of liter, all of them have, but I'm not sure if BGC, biogeochemistry, has some data set. Someone has to develop it using AI/ML, perhaps, as far in my knowledge.
Okay, thank you. So we will move on to our next speaker, who is Dmitry. If you're happy to present, please.
Yes, please. Can I share my screen? Good morning, everyone. In my presentation about West Scotland modeling system, WeStCOMS, I will try to address all three questions imposed by David about missing terms and best practice, about resources required to set up coastal forecasting system, and our method of documentation. So details of the operational WeStCOMS systems are provided on this website, where you can click on a button and get access to all publicly accessible resources. So we started to develop these operational systems about 12-13 years ago with small fjord next door to SAMS in Scotland, which is Loch Etive, and quickly get to conclusions that regular grid models are incapable to address all circulation issues within the loch with sufficient enough resolution to run on small capacity local resources. It would require substantially bigger machine to complete the forecasting cycle within 24 hours. And solution was to implement unstructured grid model, which is based on WeStCOMS, now FVCOM, finite volume coastal ocean modeling system. It has triangular mesh, 11 layers, and about 100,000 nodes. And we run it in combination with atmospheric system, and I will describe in my presentation 5 steps: setting up, running the operations, forcing model based on atmospheric weather research forecasting system, freshwater calculations to feed the basin with freshwater discharge, and some examples of validations and applications. So in the core of the system is the Fortran code based on FVCOM with substantial additions to the code to fit the local forcing data acquired from external resources and to our dissemination system on Thread server. So to feed atmospheric model, regional atmospheric model, we are taking data from global forecast system, NOAA and SEP, every 3 hours in future, 240 hours forecasts. And we feed it to 3 layers, 3 domains nested, the local WRF weather system. For open boundary conditions, we're taking data either from Northeast Atlantic ROMS model with 2 kilometer resolution, or from Mercator model. And since last couple years, we introduced data feed from CMEMS with the 1.5 kilometer AMM model run by Met Office. And for tidal model, we are using Oregon State University solution, European solution, 2008 feed, and freshwater input is calculated using the catchment area and rain precipitation and evapotranspiration factors. We are using this model to run, and the latest update was the wave model operational forecast since 2021. And several applications were developed in past years, and we are working on other listed here, like biological models, ERCM, sediment transport model, search model, and non-hydrostatic development. But this work are in a progress. The system operations are described on this flow diagram. And in beginning, start with traditionally with data acquisition from supplier websites. Then we launch our WRF forecast. It takes about 15 hours, between 14 and 16 hours for week forward. And then we update our lateral boundary data from all three listed models. We calculate reverse output, and we feed actually both WRF model and our forcing with sea surface data from JPL NASA 1 kilometer resolution multi-satellite ultra high resolution product. Then we start our runs in high cast mode with 1 day behind, and upon completion in about 10 hours we get to the stage for archive and uploading the results onto thread server. And on the right side you can see our small cluster existing. The advantages for dispersal modeling and all applications are listed here on this slide. And first of all is resolution of atmospheric forcing. It's comparable with terrain scale, narrow glens, and in highlands. Coastline is very long in Scotland. It's second long after Norway in Europe. And it's complicated. Wind pattern is very complicated in region because of tunneling effect and so on. Fresh water derived, as I explained, with rainfall over catchment area. Open boundary supply from CMMs based and near-ROMS applications substantially improved in recent years, and it's much better now. And finally, waves models. A few examples. This is the heavy storm in 2016, and I illustrated the atmospheric model predictions at 3 domains: 18 kilometers, 6 kilometers, and 2 kilometers. And we are using to drive our model with 2 kilometers domain, which is shown on this left corner. With full grid scale. And on this picture, you can compare the model. Blue and red is the observations from one of the weather stations in the region. And comparison is pretty much good. And this is another illustration for 2015 experiments from 4 airports. Red is, this case, is Met Office weather stations, and blue is the WRF weather predictions. Wind at 10 meters height. On weekend, I try to extract the latest predictions from our model, and you can see here is there was a quite essential depression arrived to the region in the beginning of October, and again resolution around SAMS is shown here. Freshwater input. There is a substantial variability in rainfall in around UK and in Scotland, and variations are substantial, between 50 and 80%. For each month in compared to 30 years average, and similar is applicable for reverse flow in different years. There is 2 contrasting years, very wet 21 and quite dry 2022, with 150% discharging compared to average, right? And this has substantial implications for surface layer flow in fjords, and we built up catchments area for each river. It's about 226 rivers for our WeStCOMS domain. And we calculate the precipitation over each grid cell in WRF and put it into basin. Some basins are controlled by hydroelectric schemes, and that put complexity because not always data are shared with us about freshets and discharge via the man-made structures. And here is the example of the surface salinity distribution in region around SCOMS, again, locative and Firth of Long, under different wind direction, and you can see that the pattern would be substantially different. Example of data validation technique, we had several moorings in past, some of them beached under certain conditions, either heavy weather or curiosity of fishermen. And currently, the main tool for data validation exercise is the launch of gliders. And here is the tracks of gliders, and this is the velocity derived from gliders, red, and model predictions, vertical average velocity predictions from the model. You can see there is no any lag in the system. This is another example with temperature, salinity, and density distribution derived from gliders and compared against model. And the job is pretty good with sometimes speed deviation in range of only few 1 or 2 tenths of centimeters per second, right? Our latest addition to the system was the introduction of the wave modeling, and here is one of the most recent late September, beginning of October example, and you can see that the geometric flexibility of the grid can prove substantial deviation from the average, and model predictions are quite detailed for the area. And this is a comparison between CIFA's wave buoy and our SWAN implementation for region, or for one of the buoy in the area and for another one. Most of the time, predictions are deviations are relatively small, but sometimes model underestimate or overestimate the wave height, and however directions are pretty good. And this is the location of the sampling points provided by CIFA website, and you can download it manually for comparison. And this is another heavy storm in usually it's in winter, and the difference between model predictions and observations was about 20 centimeters, 10-20 centimeters in wave height, and directions of few degrees. And I think it's a substantially good contribution to for dispersal studies, if we include the Stokes drift in predictions. And the other application recently developed was to evaluate local wave climate inside the fjords for seaweed growing industry, which just started to develop in the region. With support from small projects, Global Seaweed and other projects, we managed to build up 1 year and now the 2nd year of predictions for local wave climate and location of the seaweed growing farms in the area. For modeled and dispersal predictions, it's quite important to have adequate response of the model to external forcing. And you can see that if we apply high resolution WRF model to this system instead of a regular grid where we products with big tiles, 25 kilometers or 12 kilometers product like ERCM or GFS, then you will get quite accurate predictions about grid scale, 50 meters in our case, and several hundred meters in opposite occasions for the currents inside small embayment or fjords. And this is the example of hub spreading forecasts. One occasion was notified either from satellite products. We, in partnership with Plymouth Marine Laboratory, Andrew Kurechin and Peter Miller provide us with this. And the other product is Food Standard Agency monitoring program with weekly samples analyzed at SAMS. And as soon as we get harmful algae notification, we can launch predictions, spreading predictions with the severity of the bloom and arrival and timing of the particles to certain locations to mitigate for providing stakeholders sufficient time for mitigation measures. And I would say that this was one of the major drivers of forecasting system development, and the list of funding bodies and collaborators are shown on this slide with appreciation. And these predictions are available on hubreports.org website in usual user-friendly way, and stakeholders can access it with even mobile applications. And we developed similar system to run in Malaysia, and it's running now for several years there. And finally, summary. Operational WeStCOMS runs consists of two parallel systems, hindcast and 2 forecasts per week due to capacity of our computing system. It's easy to add any spreading forecast and nesting subdomains as shown here with the Bora spreading down from the Coronarus Fort William area to along the west coast of Bologna. We developed uncertainty skills assessment regular as soon as the data are provided, and user-friendly interface either via hubreports.org or our threats server system. And finally, list of publications and applications developed recently, and our system descriptions are summarized here. And you can see that there is a plastic spreading studies, biophysical modeling of larvae spreading in Scotland, and many other applications. Thank you very much. I can stop sharing my screen and happy to answer questions.
Yeah, thank you. Yes, any questions, please put them in the chat as usual. I will ask one which I may regret asking here, but the Met Office AMM15 forecasting system that you use for boundary conditions, does that meet your needs, or do you have further requirements you would like to see from it?
I think it's in the beginning there was issues, and after approximately half a year, most of the issues were sorted, and I'm quite happy with the resolution of the model to fit our open boundaries. And the only issue is stability. Sometimes when I pick up boundary forcing a bit, it's not yet ready. So the schedule is fluctuating sometimes for predictions. Otherwise, it's okay. It's very good, I think. And freshwater, I don't know how you manage to feed the model with much more accurate freshwater input. In compared to previous runs, it was essentially different, and now it's very good.
Yeah. Okay, thank you. That's good to hear, and I'll pass on your feedback about the reliability.
Yes, thank you very much.
I can't see any more questions, so if we move on to our next speaker, Regina, if you're happy to present.
My presentation this morning will be on Met Ocean forecasting in the Gulf of Guinea, status and challenges. That's the region, the Gulf of Guinea region, which we have 5 countries that I'll be talking about. And the length of the coastline is approximately 1,540 kilometers. And the morphology is such that the whole place is low-lying and has an extensive barrier system which runs from the Ivory Coast to the Nigerian coastal environment. And it comprises barrier islands, deltas, and some rocky terrain in Ghana, and relatively flat coastal plain. The whole coastal morphology is determined by coastal dynamics and drainage. The beaches are erosive. They lack sediment flow because most of the rivers are dammed and sediments are not coming. So the longshore current is not effective because of the establishment of ports and harbors. You know, we have more than 10 lining up the whole of the coastal environment. The economy is driven in large part by exploitable natural resources, as written above. And the prominent coastal infrastructure that is causing a lot of harm to the region is the establishment of different ports and harbors lining up the whole place. There is no thought of integrating the ports, so they're receiving additional ports and harbors proposed. Therefore, the challenges we are having emanate from natural and anthropogenic. And naturally, we have the Met-ocean interactions leading to coastal erosion. That is specifically the intense tidal waves and storm surges that affect the place. Anthropogenic factors are the exploitation of the resources that abound. Henceforth, we have unsustainable land use widespread. Then other challenges that degrade the coastal environment are as a result of the human livelihoods, the human activities that affect the livelihoods and well-being of the people. Sea level rise is also a factor due to climate change, and this will decimate further the biodiversity, cultural heritage, and the livelihoods. So morphologically, I'm going to be talking about the morphology, the Met-ocean characteristics. The coastline has several estuaries from chains of complexes. Erosion is widespread because of exposed coastline and sheltered areas, which is the bay, the estuaries, and the lagoons. And the coastline is determined by the coastal dynamics and drainage. Beaches are erosive due to lack of sand, as I mentioned, and the longshore process, which is affected by the human activities. The meteorology regime of the area is that we have the tropical climate, meaning the rainfall is between May and November. Winds are usually southwesterly. The speed is between 2 to 7 meters per second. But in extreme conditions, we can have wind speed being between 10 and 16 meters per second. And the oceanographic regime is such that the waves are wind generated southwesterly, tides approach southwest, they are semi-diurnal with 2 inequalities. Atmospheric forcing of the Gulf of Guinea is very regular and subjected to sudden astronomical changes and the ocean currents. So what is at the fore of this presentation is the storm surges that are rampant every year. The characteristics of the storms is such that they occur between April to May and August to October, which we have classified as the oceanographic season. And we need a tide gauge to see, the peaks, because the peaks of storm surges are marked by, spikes on the tide gauge reading. Astronomical high tide levels are usually 1.4 to 2.5 above the normal high tide. There is also a drop in the barometric pressure from 1014 to 1008 MB. We have come to this decision because of a little attempt at modeling the characteristics of storm surges in the West African region, which I was part of. I had training from that during the Odin Africa phase and then the modeling class. So the characteristics of the storm surges is such that, as I said, we have sudden increase in water level, very sudden that, it takes everybody by surprise. We have high wave dynamics, that is from 3 meters to 5 meters, and the period is ranging between 15 and 20 seconds. Then we have large inundation, exacerbation, coastal erosion, flooding, and then saltwater inclusion, salt intrusion into the coastal aquifer. The flooding and the surge are such that the communities everywhere along the coast are desperate for answers, which we do not seem to provide, because this flood of water, as I mentioned before, are quite sudden. So understanding the concept of marine forecasting is that it's a practice of predicting what will happen in the future by taking into consideration events in the past and present. Then decision-making tools that assist stakeholders cope with impacts of uncertainty is by examining historical data and trends. We rely on remote sense and in-situ observation networks and their sustainability. So developing a service for ocean monitoring and forecasting, we need to provide access to a range of observation-based and model-based products. And we should have connections with other systems in the region dealing with observation, monitoring, and forecasting to make it holistic. Odin Africa, in the past, has been a project that has provided many countries in Africa, including those in the Gulf of Guinea, the needed capacity and facilities for an effective data and information for collation and exchange. So many countries in the Gulf of region have data and information centers which have collated such historical data, and that is needed for forecasting. The training that Odin Africa gave through the IOC, UNESCO, and then government of Flanders comprise different ocean data, even giving of facilities like tide gauges, and establishing the ocean experts, which will be a link for professionals to interact. They also enable the Marine Atlas, whereby continental scale online resources of public domain geospatial data for the support of coastal and marine research and management in Africa. These training were undertaken, and most of the scientists in the region were part of it. Now, other activities in the region that comprise getting ready for forecast of the Met Ocean conditions are, for example, in other higher institutions. In the Benin, we have a UNESCO chair, and we have 3 students who are involved in operational oceanography and forecasting. We have 4 students in data analysis. We have a PhD student in modeling, forecast, and prediction. Some of their success stories is implementation of Telemark Tomahawk, which is early warning system, predicting wave propagation, wave heights, wave direction, implementation of models for wave agitation and propagation, impact study for the relocation of future fishing ports, and implementation of MIC model for sediment transport at the Cotonou port. There is an aspect which I did not really bring on board, which is the development of the sea state. This is meant for the fisher folks by the GMES project, that is Global Monitoring and Environment for Africa, Security in Africa. And this is an African Union and a European Union using Earth observation. They have developed a system of warning fisher folks about the sea state. And this has not gone totally regional. That is why I have not talked about it completely. The challenges we are faced here is the lack of tide gauges, because the tide gauges that are provided are at the mercy of the storm surges that we do experience annually, sometimes twice in a year. And they erode it and totally remove it from their locations. And with this, we are not able to see water level, the spikes in the water level, or the approach of high water levels. Other aspect of our challenge in the region is data from research vessels, POS, and then the maintaining of networks for collecting in-situ surface data is not totally in place. And operating and maintaining sea level networks is also not the best. So we lack monitoring and forecasting centers in the Gulf of the Guinea region. These are some of our challenges. Now, these challenges are leading to implementation of wrong decisions in the region. For example, establishing coastal defense systems in Lagos, which, you know, the engineers did not really understand the nature of the morphology and the Met-ocean interactions. In conclusion, I'll say that we need to understand the set of transformation in the coastal environment driven by interwoven socioeconomic and natural processes, which require a continuous in-situ measurement in all the aspects of the environment. Countries within the Gulf of Guinea are facing several challenges in forecasting oceanographic events because of scarce human and technical capacities. This inhibits strength and values for forecasting. Management of the oceans and coasts in the Gulf of Guinea require the basic ingredients for monitoring and forecasting coastal events and extremities. Ocean Africa has provided in the past capacity for scientists and coastal managers, as well as creating the enabling environment for forecasting. There is a plan for the new Ocean Africa program, and this could assist in strengthening, again, the capacity in the region, because most of the scientists that the program assisted, most of them have retired and others have relocated to other places. So there will be need for the program to bring again this aspect of strengthening capacity in the scientists and the staff. So that is all I have. Thank you for your kind attention.
Thank you very much. Very interesting. Yeah, any questions, please put them in the chat. A question from me, thinking in particular about the storm surge forecasting, where you have a quick emergency response needed. Would you prefer to see something on a regional scale covering all countries around the Gulf of Guinea with a single system, or a more national level implementation?
Okay, I think we need to have a regional outlook. That is, the scale should cover the region, because there isn't much demarcation in the whole of the coastline. It is a one barrier lagoon system, meaning that behind the ocean, or this in front of the ocean is the lagoon system, and you can travel with a boat all the way from Cote d'Ivoire to Nigeria. So it's all low-lying. It's the same process. And the longshore current system is such that it carries sediments from the west to the east. It is the same process. So having it country by country will not solve the situation. We need to see what is happening in Nigeria, because from Nigeria, it will now translate to other regions. That is if the weather system is coming from the east. So we'll need a regional approach to this issue.
Okay, that makes a lot of sense. I can't see any more questions, so if we move on to our next speaker, Nadia.
And I just heard the last speaker. I congratulate for the enormous advancement done for the Gulf of Guinea. I'd like to make a comment with respect to national and regional. They're both needed, because you need to have a nation that is self-sustaining in its protection of the sea. At the same time, you need the regional approach if you connect it to very coastal needs. So let me give my presentation. Okay, so let me see if I can have full screen. Can you see now?
Yes, can.
Okay, so I tried to overview a little bit my latest thoughts on best practices for coastal limited area predictions, which are part of this CoastPredict UN Decade program that we are trying to define also with the program itself. So we have best practices at this point in the ocean. Here I show you the example of the Copernicus system. We have open and free access to 1 to 5 kilometer scales, hours and days, observing and forecasting for major essential ocean variables, such as waves, currents, sea level, sea ice, and biogeochemistry. And we have a service that will discover and allow free and open download. So I find this system rather unique, and showing best practices in the field. It is rather new. It was developed in the past, I would say, 6 or 7 years as an operational system before it was developed under research and development funding, and now it is operational. This also progression from research to operation is something that needed, I think, in each country too. So here I'd like to now tell you what is the near future, and is this seamless? Best practices and standards on how to do the seamless are not available, but let's see the movie now for a second. Okay, and so on, meaning that what is now we can reach every structure that we have on the coast and inland connected to the coast. The point is that we developed up to the regional some standards and a lot of best practices, but we still have to understand well how to do the last mile. Okay, so we thought that one best practice is to go around to try to define by the decade what is the global coastal ocean, and actually take the approach of the global coastal ocean, because problems are common. They might show in different components, but they're common. And what we have presently a non-uniform terminology. And I think a best practice would be at the end of the decade to have a common definition. And the common definition is that we have to include the land as far as is needed for predictive capabilities. So I heard very marginally at the end the comment on river inputs, how to get hydrology and hydrological community work with us. This is a very important point. And then arrive offshore where is needed. So let's jump now to the issues of what, some point, what is required to advance the seamless ocean of the global coast, in the global coastal ocean. We need to have comprehensive digital terrain models and bathymetric information. This is a key when we have, the complexity of the coastal area. And here we have made several attempts in the past 10 years, still to be updated and ameliorated, but I find this my first point: high resolution digital terrain models. Second is the river, the estuarine, urban inputs. Here we are much farther back in best practices. We need water and loading, monitoring and forecasting, and that is still something done case by case without a standard. Now it is possible. And the basic initialization, lateral boundary condition data and methods for waves, tides, biogeochemistry, sediments and currents in a limited area model in order to get the correct information from offshore to inshore. And last but not least, the atmospheric forcing. I have to say that the atmospheric community is the least convinced that this is, a very important point. And at the moment is the least involved in open and free exchange of forecast, as well as chemical inputs by atmospheric forcing, because our ocean, not receiving any more river waters, is fertilized by atmospheric deposition. Okay, so we have to consider issue one. Sea level at the coast is due in most part of the global ocean, is due to the regimes offshore. In this wonderful paper, which I recommend everybody to read, they make a clear case on so many coastal areas of the importance of the offshore flow field for extremes in sea level. And what is the gap here is that observations and model are not yet integrated in terms of scales and processes to capture that offshore important signals. The other one, issue two, is the integration with the river modeling. River monitoring and modeling should become a component of coastal modeling in the definition of the new global coastal ocean. They are not separate. And here you see an example of in the US East Coast, Savannah in Georgia, where we can predict now salt wedges and salt intrusions due to the detailed knowledge of the DTM and the coupling between the offshore and the river. So another issue is in the coastal area that we have to keep considering and start more efficiently is the uncertainties estimation, because if we have uncertainties in the open ocean in our forecasts, that we have many more in the inshore. Here you see recent new ensemble forecast for this area on the Po River, where an unstructured grid model is being forced by many offshore models, many atmospheric forcings, and many river inputs. And you see this is for sea level. With 45 ensemble members, we are able to really get close to the observations with the ensemble mean. Okay, so we have to consider from the start the uncertainties for our area in the coastal area, the coastal ocean. So another very major point, I think that at least this we could probably try to advance is to have best practices for calibration and validation of our coastal models in order to get high fidelity coastal models that are needed for digital twins and so on. And here we have an example where we did the exercise, and this is a model that is nested into the regional model that is high resolution in the area that is needed. The Taranto that you have seen before, and here you show we only when we could show that observations are best fit by the nested model, even against a coarse resolution with data assimilation. We trusted our model. And trusting models in these complex environments is a big part of getting the right answer. Okay, so I conclude by saying that my list of major gaps in best practices for coastal predictions is, first of all, the availability of coarser scale regional global model analysis and predictions. In Copernicus, we have regional models that are European regional models, but I believe also with the previous discussion that you need a two-way approach, two-way downscaling approach to the coast, from the global to the coastal. We need to get the model standards for relocatable model, limited area models, which domain size, which kind of resolution increase toward the coast, etc., for not talking about vertical resolution, and then observational coastal data to validate, calibrate the models, river water discharge and chemicals, sediment loading observations and predictions. We are particularly weak on that. Rivers are not monitored for sediments, for chemicals, even for salinity, they are not monitored. So we need to jump into the AI-based models for impact forecasting. And we have absolutely nothing here on best practices. We need to go ensemble forecasting to control uncertainties, and we need to establish coastal digital twin best practices that somehow come, in my opinion, after the others, but people can put the order that is more suitable for their scope. So thank you very much.
Thank you, That was an extremely informative summary of a lot of the issues I was hoping to get out of this session. If anyone has any questions, please put them in the chat. I was just wanting to pick up on your point about trusting the models. Do you feel that stakeholders don't trust models maybe as much as they do observations or weather forecasts, or do you think they are very ready to accept models if given them in a way they can use?
Well, they don't trust it now. In fact, I think they're much more, the practice of operational meteorology has worked for many more years than in oceanography. So they're much readier to trust an atmospheric model. If this is your question, atmospheric model, then they are to trust a coastal model. Also, we have, it was mentioned, we have in the past had an engineering community practice that was mainly connected to observations. They tried to deny the importance of, I think my practice, at least too much, the importance of models to find solutions. But this is changing. Yeah, so trust is not yet at the level that we should have. And it is also due to the fact that we don't have a best practice in model validation, and that this best practice in model validation should be continuous. It's not that you can demonstrate in one event that you are successful. So it is a monitoring, coastal monitoring for validation calibration that is actually a new, probably a new avenue that we can undertake to get more trust. Yeah.
Okay. Thank you. Got some questions in the chat. Don't know if we can get through all of them, but first one from Jay. If you had less computational capabilities, what would you lose in coastal forecasting?
Yeah. So this is a very good question. I think we have options now. And the options are that we have availability of cloud computing. And that should be ensured by a larger governmental agreement that should be made available. We have already Google Earth Engine and Planetary Computer that offers a wonderful cloud computing framework that could be used in place of local capabilities. I think we should jump directly to that. It's too hard to do the old technology and then come through all the problems that we had in some countries to arrive at operations, and now we can use the new dimension. Oh, it's a bit of a dream, but that's fine.
Okay, then a question from Fraser. In some cases where best practices are needed, do we need to rely on other organizations, such as the IHO for high-level coastal bathymetry, or is there a need for oceanographers to engage on this or interact with relevant organizations?
Yeah, thank you, Fraser. I think that the best way should be to, at the same time, IHO is a very important organization with a very good set of rules and best practices that has saved us from not having anything in the past. I think that in terms of UNESCO IOC, IHO should be much more consulted at the level of member states, and member states should acknowledge the importance of hydrographic offices in getting the data in the public and open free access. This is, I think, is not as difficult of a process as, for example, for atmospheric forcing, at least to my experience.
Okay, and one final question from Anita. Could you please comment on nesting coastal models, unstructured grid with structured grid open ocean models? Is this feasible?
Yeah, it is totally feasible. We have now shown many regions. The one I have shown you are all unstructured. This is an unstructured grid model nested into a regional Copernicus model. The one in here is also unstructured. This is a US East Coast, and I would have many others to show you. Totally feasible. However, again, and this is part of my list of priorities for best practices, we never discuss how to do that. We have several good, practices now in the field, and it works. There is no reason why it shouldn't work, first of all, but I can assure you that it works. And it should be, I think, the right technology for this kind of global coastal ocean problem.
Okay, thank you. Frave have posted another question, but in the interest of time, I think if you could please try and answer that in the chat, and we will move on to our final speaker, who is Enrique.
Thank you. Thank you for the opportunity of sharing some time with you today. And I will start explaining a little bit what we pretend to do at OceanPrediction DCC, and at the end I will naturally follow into the aspects related with best practices. So what we pretend to do is summarize in this slide that some of you might have seen already. This is what we have today, the ocean forecasting we have today. We are proud of the systems that we have, but we have to admit that those systems are not as frequent, as ubiquitous as we want, and they are hard to maintain, hard to install, hard to operate, and they are not sharing many of the things that could be sharing. There is therefore a poor presence on those institutions that are technologically less advanced. And we want to change this to a different scenario where we have, first of all, a connected community that will be able to support all these activities, and then many more systems that will be more reliable because they will be using common tools, common architecture, and common things such as the digital twins that will reinforce all the data interoperability. So to do this very ambitious transformation, of course, the captain who is leading this process is the decade. We count very heavily on the decade actions, on the decade programs, such as CostPredict, as Nadia was presenting before, 4C, DITO, and many others, for advancing in this direction. And also we count with the arrival of the digital twins as a key element to do this transformation. Who is going to be with us in this change is the community that we are building around OceanPrediction DCC, and our role will be to serve as inspiration. Is the role that the decade has assigned to us, to serve as inspiration, that the decade coordination unit has assigned to us, to serve as inspiration, as guide from moving from one scenario to the other. So what do we have to do this transformation? This is the assets that we have today in different degree of development. Some of them are fully closed, fully developed. Other of them are in development at this moment. So these are the assets we have to build this transformation during the decade. First of all, we have a technical framework with a team of experts. I will explain all this during the presentation. A technical architecture that should serve as base for this development. Then we have a community organized around regional teams. We will build an atlas of operational forecasting services. We are starting to develop a plan for capacity development that will be heavily relying on the TÜV's guide, which is, I hope that you have heard about this publication. We published this last year. On the technical architecture that we are building, a TÜV's guide will be like the theory book. The technical architecture will be like the practice book on how to build system, and on several educational activities based on these two. And then, of course, with the collaboration with the decades actions, aligning our vision and aligning the vision of the different decade actions, working on this architecture development and developing a series of shared actions. So those are the tools, and I will explain a little bit those tools and how this leads to the best practices.
Let's go to this.
Oh, sorry. This one has some recording on it. Sorry about that. Okay, there we go. So now without recording, I mentioned this technical team. This technical team is already in place, and we are working exactly to fill this gap that I already mentioned before. The fact that the systems are somehow technically disconnected, and this is evident during all phases of the process. During the development, the new systems don't have the right tools to be developed fast, and during the exploitation, you don't have the possibility to use common tools for validation, dissemination, and exploitation. So this is dragging the development of additional systems worldwide. So the opportunity is the decade and the arrival of the digital twins that will change this scenario. We cannot change this. This is very challenging. We cannot change this in 2 days. So the first thing we have done is to build this ocean forecasting co-design team that is working on an architecture. And in fact, we are quite advanced in this work based on data standards, tools, and best practices. And here we start talking about best practices in cooperation with related decade programs. So the idea is that this architecture will inspire decade program development targets. This is the idea behind this. So I was mentioning you don't have to look into the details of this slide. This is just to illustrate that we are advancing well with the definition of these, let's say, standard architectures. And we have come to 3 main families, 3 main models, which are called A, B, and C. And these are changing depending on the role of the digital twin in the model. This Ocean Prediction A is very similar to what has been developed during the years in the Copernicus Marine Service that Nadia was mentioning before. So here we don't have digital twin, but the system is still interoperable thanks to a layer here of interoperability. Well, this is the classical ocean forecasting value chain. The Ocean Prediction B architecture, here we have the arrival of the digital twin, but the digital twin is considered here as a tool to facilitate the integration and the interoperability. And the Ocean Prediction C is where you have a full digital twin and you have all the forecasting engines already included on the digital twin. Based on these 3 architectures, we are going, this is even less for looking into the detail. Please don't look into the details of this. But we are developing a series of wiring diagrams that will then fit into these 3 mentioned architectures before. So this is, for example, the wiring diagram on how observations are accessed into the system, into the different models. And here there are some, this is quite technical for now, but this is just to illustrate how this fits into the 3 different architectures ABC. So all these wiring diagrams are dropped, let's say, into these 3 architectures, and this work is already done. So we are talking here all the time about tools and data standards. When we use here in this context of Ocean Prediction DCC the word standard, we are always referring to data standard. So first of all, we want to understand what is a data standard. And we came with this by looking into ETIL and in other places. We came to this definition of what an ocean data standard must have. This is both for observations and for results of numerical models and all the pieces connecting both things. First of all, we have the FAIR, which is very well known. But now we have also this that defines, when we're going to define the data standards, what do we have here? We have a format, NetCDF is the classical one, the metadata, the lexicon, what if we're talking about SST, what is exactly SST? And then we have the storage organization, how the data, for example, talking about sea level data, are we collecting all the data into daily files? Are we using monthly files? How the information is stored? What are the options for that? And once you have all this done, you need also to define an API to connect this to the rest of the world. So this is what, when in all these diagrams, you see these data standards in blue, this is what we want to define for these data standards. We don't define all of them at once because there are many of them, but we will instead highlight the more important ones and start in there. And this is where we need also the collaboration of the decade actions. The operational readiness level. Sorry again, this problem with the recording. Sorry about that. Another concept which is important for this is the operational readiness level. This is basically something that we are starting to develop now. And it's a series of numbers that try to define exactly that, how operational a system is. These are 4 independent digits. The first one stands for the degree of operationality, the second two, the fit for purpose of the technical solution, the third one for the degree of validation, and the fourth one tells how good is the dissemination of the data that you are doing. If we are able to develop and implement that, this will promote the adoption of tools, standards, and best practices. It will be a mechanism to endorse services to join common framework, and also a way to stimulate service development. So somebody can see that maybe one of the numbers is not good enough, they know where to develop further the system. So how all this fits on the best practices concept. Once architecture and operational ready will be ready, best practices could be more easily designed with 2 objectives. First, to support this implementation of system based on the shared architecture. So best practice could be, please use this agreed format, this agreed data standard, which consists on these components that I mentioned, as a best practice to promote the interoperability of your data. That could be one of them. And it will also help to create robust and reliable system based on the use of the operational readiness level, as I explained on the previous slide. Also, these best practices, these ORL and these data standards are deeply linked with capacity development strategy that has to be linked with those. As I mentioned, we have on one hand the tools, we have on the other hand the architectures. So we have all the elements to build capacity development activities based on those. The other pillar is the regional teams that we are implementing. So once we have this, how do we implement it? How do we go to the real world and start talking to the people how we implement all this? So the regional teams will be a key element for this. What we have is taking the best of the United Regional Seas and the good regional alliances. We have divided the world in different regions, and this we are creating teams on these different regions, and this will be our boots on the ground for many things like capacity building, identify gaps and way forward. But very importantly, to advocate for the implementation of these best practices, data standards, and tools that I have been talking about. So we are doing very well. We have chairs in all the regions. We have steering teams in most of the regions. We are finishing. The objective is to have these regional teams built by the end of the year. And we have all these additional assets, such as, for example, the Atlas of Operational Forecasting Systems. We will launch our webpage before the end of the year also. And we will build also inside the webpage an atlas with all the operational systems around the globe. Regional teams will help us to include all these regional systems. And as you have seen on the previous image here, you can introduce yourself the data information into your system. So this will be sustained by the developers of the systems. So once all this is done, another key element is the endorsement. So here, what we plan to do is working in close collaboration with WUS, more particularly with the TÜVs, to generate an endorsement mechanism that is allowing us to, once we have a standard define it. So the idea here is the OceanPrediction DCC in collaboration with decade actions such as CostPredict identifies the needs of a new standard tool and coordinates the co-design of the specifications. The decade actions develop the new component, align it with these specifications, and finally it is a TÜV, the one endorsing this component. So as conclusions, the work we were trying to do, we hope it's going to be a key element for the ocean prediction we need. We are going to work in collaboration with a large community of users, scientists, and policymakers. We want to take advantage of the framework of the decade and the arrival of the digital twin of the ocean as a key element for interoperability and more to join and deliver together worldwide. If we succeed, even if we only succeed partially, substantial benefits are expected, such as a connected community, more abundant and better operational forecasting service, and a technologically linked worldwide ocean forecasting framework. We are fully aware that this is a significant challenge, and it's only possible through collaboration with dedicated programs and other relevant actors. So this is it on my side, and I'm glad if you have any questions to reply to those.
Thank you very much. And yeah, as usual, please put any questions in the chat. One from me, you talked about best practice for data standard for the API. Do you plan to just do that at the API level, or also for more end user presentations such as website, smartphone app, or other things, or is that beyond the scope of the DCC?
So the reference to API here goes literally to the standard definition of what is a data standard. If you go to ITIL and other sources of people that is working this in different contexts beyond the ocean forecasting or the oceanography in general, you see that one of the components of the data standard today is considered the API to connect this data standard to the rest of the world. So this is, by definition of data standard, what you need to connect this to the other elements of the value chain.
Okay, thanks. Got a question from Nadia. How do you plan to get atmospheric forcing from numerical weather prediction?
Nadia, there's another of these diagrams exactly devoted to this. So it's not an easy thing to answer without pen and paper, I think, technically. But I don't know if you mean technically or you mean politically.
No, I mean, it's more political, right?
Okay, politically. Okay, I think that we have to do not go maybe into that, because I think that each region will have their own sources and they will have their own data providers.
Yeah, we say so, but even as it's difficult to get.
Oh yeah, it's a big issue.
A question from Jay. You mentioned best practices for data. Do you envision best practices and standards for models?
What? I don't know. I don't know. Maybe I was very, very fast on my presentation. I tried to pack maybe too many things. Sorry about that. When I'm talking about best practices here, the idea is, I mean, there's a little bit of confusion on when you start reading about the concept of best practices and the standard, because the standard is not always refer to what we are talking here. We are asking ourselves only talk about data standards. So first of all, best practices is more associated to processes here, and the standards in our world is limited to data standards, just to clarify the situation. Then what we believe standards are going to be are the procedures, the recommendations, best practices are going to be the procedures, the recommendations on how to implement all these developments, all this architecture, all these tools, all these standards, whatever we manage to define or build, how we are going to implement it, and how you are going to improve through this operational readiness level staircase. This is what is the reign of the standards in our world.
Okay, thank you. So we're at 5 minutes to the hour in my time, so slightly inevitably in my enthusiasm to fit in as many interesting speakers as possible, we don't have a lot of time for open discussion. But if any of the panelists have anything they want to raise, or without wanting to put you on the spot too much, Jay, I don't know if you have anything you want to say at this point.
Yeah, thank you very much, David. I think the support of the modeling and operational community with the best practices, with the best practice repository, is something that we need to work on together. The development of the best practices in this area is a priority as we work through the value chain from observations to end users. We've had a lot of good discussions today, both in the forecasting, but also in the end user elements. And I want to thank the speakers for that.
Okay, thank you. I will actually, if we don't mind going back to Enrique, we've got one more question in the Q&A. At this stage, is the design considering also standard for the interoperability among workflows to make possible the implementation of longer data value chains, starting from smaller workflows which are already in place?
So I was not able to get to the question. Can you please repeat?
So it's in the Q&A.
Okay.
Is the design considering also standards for the interoperability among workflows, so to make possible the implementation of longer data value chains, starting from smaller workflows which are already in place?
So I'm not 100% if I understand the question, but something that we certainly want to do is avoid reinventing the wheel. And we are, let's say, starting to define this architecture, let's say, from somehow scratch, but then at all moment, all these tools and standards that we are putting on the blueprints, we are always trying to ask ourselves, and we are open to this, if there are any data standard or any tool that could be already available and could do this work. So, and obviously something that we cannot do is to develop all this in one go. So we have to define priorities of where to start. We have to define which are the data standards where we have to concentrate our effort initially. And then I think that this will allow somehow to do what Massimiliano is suggesting, of working with smaller pieces that make possible the implementation of longer data value chains. So I hope I replied the question, although I do not fully understand 100%, but I hope it's in that line.
Okay, thank you very much. With that, I guess we should draw things to a close. I would like to say a massive thank you to all the speakers and everyone who's contributed. Personally, I found this all extremely interesting and useful, so I very much hope other people have done as well. And this should all be part of an ongoing conversation and discussion among various groups, particularly in the context of the Ocean Decade and the Ocean Best Practices. So I hope to see and hear from you all more in future. So with that, thank you very much and have a very nice afternoon, rest of your day.